So this will be lecture 4 of Harvey Friedman's treatment of tangible incompleteness. So Harvey, please.
Thank you. This is lecture 4, in which I finally start proving some of the statements. And this time, I'm only going to prove the statements, and there's a group of them. I'm only going to prove the statements that can be done in ZF, and they, in fact, all will be provable. The proofs will be in Zermelo. And then next time, I'm going to do the proof of the strongest theorem considered in the book. And that one will require, that one is, I'll prove with certain large cardinals, the stationary Ramsey property cardinals, the SRP cardinals, or you can call them the subtle cardinals of finite order. They are interleaved between each other. But that one, I have a reversal. So the rest of the lecture series is concentrated on the reversal of that, which is many lectures. And I have not worked out reversals for these statements I'm giving today. I think that there's too much activity going on different fronts in this project at the moment that I'm very involved with. And they're particularly surrounding finite forms and game theoretic forms. So I haven't gotten involved in reversing the statements today, but those are important projects, of course. All right, so let's start with the simplest version. So I'm going to try to do this simple, building up a little bit more complicated and so forth. And with the simplest one, you get an idea of how they all work in some sense. Maybe not quite. There's still some more ideas. All right. So let's start with the simplest version that's not provable in RCA naught. And I don't even know, I've forgotten whether I've actually shown that this is not provable in RC naught, SCA naught, but I don't have time right now to worry about it. And I think that shouldn't be too hard to do. We're going to only use the weakest form of invariance, which is called Z plus invariance, and you'll see what I'm talking about. I got sidetracked a little bit about the reversals. These statements all reverse. Excuse me, these statements are provable in systems, but they're always provable in the light phase systems. There's no bold phase activity going on here. No bold phase activity. Of course, that's intimately related to the fact that these statements, as I indicated last time, how to show that they're implicitly pi01. So there's nothing boldface about an implicitly pi01 sentence. All right. Anyways, so the natural proofs don't use parameters. It's not surprising. The natural proof's not using parameters. All right. So anyways, this is the first statement. Now, this is not the neat way I stated all this stuff with the powerful definitions in the last lecture. This is down-to-earth shop statements. In other words, where I'm actually spelling things out without using any definitions, basically without using them. And I want to do that because we want to get into proving them. I don't want to have you keep having to remember any definitions, okay? So here is the bare bones version of the simplest one. And it's too trivial with the interval 0, 2. So I use the interval 0, 3. All right, now, this is the form. Basically, it goes like this. If I have an order, if I have, this is like a maximal root, except that I'm tearing it apart a bit. if I have a set of order types of four tuples, so E can be viewed as a set of order types of four tuples, because I really only care about the order types of the elements of E. And I write 1, 2, 3, 4 to the 4 because every tuple with natural number elements, with a positive integer elements, is order equivalent to one where it only uses 1, 2, 3, and 4 at most, right? In other words, 2, 6, 8, 200 is order equivalent to 1, 2, 3, 4, for example. So just for specifics, I mean, although it doesn't really play a role in the proof, I just say let E be a subset of 1, 2, 3, 4 to the fourth. And that also gives you an idea that perhaps you don't want to handle this stuff by hand. In other words, go through all the possible sets of four tuple order types, because there are a lot. All right, so there exists a set in 2 dimensions. This is all two dimensions. Most of the things I'm going to say today are 2 dimensions. That's not quite. That's a little bit of a lie, but you'll see what I mean. Actually, that's not quite true. But 2 dimensions is a central focus today. All right. So I can find a set in 2 dimensions, which is such that every element of S squared is order equivalent to some element of E. All right, because S is 2 dimensions, S squared is 4 dimensions. And S is maximal with respect to that condition. This is my invariant maximality. This is just invariant maximality picked apart so I can dissect it in a simple case so you can see what's going on and how to prove it. That's all. All right, so A and B are the invariant maximality, right? And C is the invariance condition. The invariance condition reads in this case, this simple case I want to do, is that if X is in the interval, is in the set consisting of 1 and 2 squared, then X is in S if and only if its shift is in S. So this is an example of a shift invariant maximality theorem. Invariant shift invariant maximality, right? Very simple a case of it. Now, you might think this is trivial from Ramsey's theorem in some sense, but it's not quite right, because when you look at X plus 1, you see that 2 can become 3, right? 2 can become 3. And 3 is very different than 2 because 3 is an endpoint, is the right endpoint. So if I actually were in the interval 0, 4, and I did this in 0, 4, and I only said C, that if I have 1, 2, I can shift it, you would easily prove this using Ramsey's theorem, because you would get some sort of maximal thing, and then you'd use Ramsey's theorem to get imposter numbers 1 and 2. They would be imposters, and then you just isomorphic the whole thing so that 1 and 2 are there. Since the whole statement is purely order theoretic. But the point is that I'm engaging the right endpoint, so there's something happening because I'm engaging the right endpoint in this invariance. All right, so we fix E as given, and we call this the E maximality condition, right? I'll call it the E maximality condition, as in invariant maximality and choice. In other words, this is the E maximality condition, right? That everything is like it has to be an E, all the pairs are pairs, and I'm maximal with respect to this property, right? And this condition makes sense for any binary relation on any linear ordering, right? Any binary relation on any linear ordering, I can ask for it to be E invariant. Makes perfectly good sense. All right. Now, getting this E maximality condition to hold is just a Just to get the maximality condition to hold, of course, is just a Zorn argument or a greedy set construction, as we discussed last time. And you can even get that to be recursive. But if we do that, we won't automatically get any invariance. It's just a wild statement that I'm going to maximize. It says nothing about invariance. Now, the same greedy argument can be strengthened with no change to be relativized this way. If I start with something with condition A, I can extend it to A and B. So if something is okay, then I can extend it to a maximal okay. And you're familiar with that all branches of logic have this. Anything good can be maximally extended to be maximally good. You don't have to start with the empty set. Now, of course, if you do that, you're going to lose all this effectivity. You might have a nice effective start, but you're not going to get an effective finish if you start with an infinite thing, because you're going to have to start asking questions, quantifying over what you have before. And no longer is what you have before just finite, as it is when you just do the greedy construction from scratch. See, so there's some quantifiers in there when you relativize this. Okay, it's a good point. All right. Now, what we're going to do is we're going to make an increasing sequence of sets, a tower of sets, and we're going to go to Q of 0 I squared, where I goes from 1 to infinity. In other words, we're going to jump out of Q03. We're not even going to start with Q03 even. Does it? Q03 will be left in the dust, okay? And all of these obey E maximality, and they each extend each one extends the previous one. Now that's a relativization kind of thing, because now let's say I finished Q04 stuff and I want to go to the Q05 stuff. Well, from the point of view of Q05, all that Q04 stuff is partial, right? Is a partial thing, and so I'm extending it, right? So that's an example of where I'm actually extending stuff, in that relativization sense. All right. And we also, when you do this, you don't get any new elements below. In other words, everything is completely coherent. All the stuff that you handled in Q05 is never going to change. You're not going to add any new elements in Q05 squared. You're not going to add any new elements later when you start dealing with Q06 and so forth, because it's already maximal. It's already maximal. All right, now we can apply Ramsey's theorem for pairs to the part of this that's integral, that's positive integral. We can apply Ramsey's theorem for pairs to get an infinite subset, any two elements of E squared of the same order type, either both lie in or both lie outside S. Okay, and that's actually overkill. You don't even need that much for this. So then I can let M be less than R be less than T be in capital E, this homogeneous set E. And then S sub T in my list of greedy constructions, maximal whatever, S sub T will be contained in Q0T squared will obey A and B. That's just saying that that's just repeating that S sub T is a maximal, what did I call them? A maximal set. And E maximal set. And we also have for every X in the doubleton MR squared, X is an ST if and only if S prime is an ST. By the Ramsey, by the packets homogeneous. Now, this is actually what we asked for, except that we now are sitting with MRT instead of 1, 2, 3. Remember, we asked for 1, 2, 3. The statement involves 1, 2, 3. All right. Right, it's just a shift of things from 1, 2. Okay. So we have these imposters that we used, MRT, in much later S's. Well, all we do is take S of t and isomorphic. In other words, map M to 1, R to 2, and T to 3. And preserve the order. Okay, and then the proof is done. The proof is done. I try to break this down into the simplest possible statement. So what did we do? We took a problem in Q03, invariant maximality, and what we did is blow up Q03. We created a hierarchy. We did this. We went all the way to Q squared by starting with interval 0, 1, then we went to interval 0, 2, went to interval 0, 3, and so forth. We built up a hierarchy, and then we picked out 3 places, convenient places, that are like what we want, except that we found them by Ramsey's theorem. Okay, so note that we only needed the finite Ramsey theorem. In fact, the finite Ramsey theorem for ordered pairs drawn from some tiny number, which I didn't bother to calculate. And so that means that all we needed really in this proof is construct finitely many S's. So we only had to go from S1 ... to S 40 billion. That's all we had to do. I mean, it's probably much smaller than that, because then we could use finite Ramsey's theorem. So we didn't really need to go all the way to the end, that much. It's overkill. But in certain invariants of this, you may want to do that, certain extensions of this. Now let's talk about what kind of axioms I needed to prove this. Well, to construct, there's nothing in the Ramsey theorem because it's finite Ramsey theorem. In fact, finite Ramsey theorem for particular numbers. So there's no strength there that was used. The strength was in the construction of the S's. The first one, S1, as I told you, is easily doable in RCA naught because the greedy construction at any stage has only finitely many things accomplished, right? So S1 is easy, that doesn't have any strength. But S2, however, is something else, because S2 has to build off of S1. S1 sits in Q01, S2 sits in Q02. So there, the obvious greedy construction has to ask a question. Can I put this in? But can I put this in is not a finite question. It's a question involving put something into S1 and then so forth. So you see there's a jump involved. There's a jump involved there. And with the construction of S3, there appears to be a double jump involved. And with the construction of S4, a triple jump involved, and so forth. Now, I didn't, as I said, I'm too busy with some more dramatic things to actually work this out, but I think you could work this out recursion theoretically. That, these are actually complete the levels of Turing degrees. There's 0 jump, 0 double jump, and 0 triple jump, and so forth. If you pick the set capital E properly. Sometimes you pick the set E of everything is very simple, right? Like, how about picking E equals the empty set or something stupid, right? So this is a kind of a nice, simple situation. I'm clearly proving this in ACA naught. In fact, I'm proving this in parameterless ACA naught, which is boldface RCA naught plus parameterless arithmetic comprehension. That's clear. For each, excuse me, I'm doing that for I'm doing that when I fix the what am I fixing? When I do that, when I'm fixing the well, in the statement though, I didn't have any parameters, so this is just proved in yeah, there's no integer parameters here, so this is just proved in I don't know 25 jumps or 2,500 jumps period or something, according to the Ramsey theme. Probably much smaller than that. Okay, so that's clear. All right. Yeah. All right. Now, here is now I'll put some parameters in and be a little bit more general. So now I'm handling, now I'm in Q0n closed to the kth power. That should be familiar because that's what I use all through the book. Q0n closed to the k. And the order types I'm interested in are order types of 2k tuples because I'm still doing this root square thing, right? So if I have a set of 2k tuples like that, I can always find a maximal gadget where this time I have a stronger invariance condition, namely that if I have x and y in the numbers 1 through n squared, x is an S if and only if y is an S. And notice that this indiscernibility only involves natural numbers, you see. This is the baby case of things. And I'm going to prove that the same way. This time I'm going to construct a large, okay, so we don't have to go infinitely many S's. We're going to construct a large tower of S's, so large that the finite Ramsey theorem that I need to do this holds with the index of how many S's I've made up. So it has the same character. So obviously this statement is provable for any fixed K and N in light-phased ACA naught. You just need so many jumps involving K and N. The number of jumps is simply connected with the finite Ramsey theorem. Excuse me, the finite Ramsey theorem for pairs. Just the finite Ramsey theorem for pairs. That's all. The general statement with K and N variables is provable in ACA prime. ACA prime is RCA naught plus, well, maybe you want to say it this way, ACA naught plus every real can be jumped any finite number of times. But since we don't want to care about boldface here, maybe RCA naught plus, yeah, RCA naught plus any, plus there's the nth jump exists for every n universally quantified. So that would be the standard proof of this. Now we know that there are other proofs of this because it's implicitly pi 0, 1, namely in WKL naught plus con of PA. I think that, yeah, that would be enough to prove this. I didn't really prepare a lecture in that direction, but I think that's what is good enough. Our WKL naught plus con of PA. And I believe that reverses, although I haven't really got into that. All right, now this is the weak kind of invariance, just involving the numbers. But there's a thing called interval invariance that we discussed a lot last time. So when I bring in interval invariance, then the whole then the thing explodes in strength. Even very modest forms of this, it absolutely explode. So here is the baby version, which the baby version which used shift invariance. This is the weakest one of all. I should tell you a little bit about this with high school students. This statement, by the way, for the high school students, I used -1, 1. There's an evolution of this. -1, 1 is trivially the same as 0, 2 because everything's order theoretic, right? So if you actually look at the papers on my website, downloadable manuscripts involving the Ross program and high school students, you'll always see the interval Q of -1, 1. All right. So let's forget about that trivial difference. This is the high school statement. And what I did for the high school students, by the way, excuse me, let me take this back. This is a variant of the high school thing. With the high school thing, I start with 1, 2, 3, 4 squared, and I ask for pairs in the set to be order equivalent to something, to some pair in the ground. Yeah. So this is actually simpler than that. In some ways, simpler, or at least not quite the same as what I did with the high school. Yeah. So, and I just want to give the story. So in the high school thing, what I was able to do is slightly different, okay, but similar. What I was able to do is prove the statement for them when E has cardinality at most 3. When capital E has cardinality at most 3. In a slightly different context. 4 was mind-bogglingly complicated, and I sent them home and haven't heard anything from them about it. But 3 already was quite detailed and difficult. But, I'm doing this by hand. I'm not using big machines. Now, we're all grown-ups, and we're going to use big machines, you see. So 3 is a far cry from the size that E can be, of course. Now, we're going to prove this using third-order arithmetic. We're going to prove this using third-order arithmetic. A weak fragment of third-order arithmetic, some sort of extension of second-order arithmetic. Now, what does this statement say? It says the same thing as I've always been saying. There's an E maximal set, but with the following invariance property. And I call this is interval shift invariance because the interval I'm interested in is the interval left close 0, right open 1, right? So for every P in that interval, P1 is an S if and only if P2 is an S. 1P is an S if and only if 2P is an S. And 1,1 is an S if and only if 2,2 is an S. This is just the unraveling of my definition of one of my definitions in the last lecture of interval shift invariance. Since the dimension is only 2, all the shift means is I can go from 1 to 2. Only 1 to 2 is the shift. And that's what all 3 of these things are saying, right? that I'm invariant when I pass from 1 to 2. All right. So how do I do this? Well, I'm not going to simply use some sort of Ramsey theorem at the end for natural numbers. What about these parameters? See, this is shift invariance. The parameters are the rationals P in the interval. So something is much more tricky here. So, but we also construct S naught contained in S1 dot dot dot. But it doesn't really help us a lot to do S naught, to do a finite construction like we did, finitely many S's. It doesn't even help us do an omega sequence of S's. We have to do omega 1 sequences of S's. We have to build the S alphas where alpha is a countable ordinal in order to do this. And we can't stay, and we also have another problem. We can't stay in anything like the rationals. We can't stay in the rationals when we're going to go transfinite with this, right? So we've got some problems. So the way we handle this situation is we use the spaces alpha cross Q01. It's important that QB have the left endpoint and the right endpoint missing. All right. These are the spaces we use. But these spaces also have to be, you have to add a point on the top. You have to add a right endpoint or else this is useless. Remember, the right endpoint is very important in this work. So we have to add on alpha comma 0 in the space T alpha. And we do this for alpha less than or equal to omega 1. Of course, the preferred one is T of omega 1, the granddaddy of them all. Is the master space, is T of omega 1. And this lexicographic ordering that we use, where Q01 is given its normal ordering, and the ordinals, of course, are, is called less than star, is the ordering. Now we can build these S alpha contained in T alpha squared yeah, I think in some later places I might not have written the exponent 2, but this time I wrote it right. S alpha contained in T alpha squared. Now remember, each element of T alpha is itself a pair, namely an ordinal comma a rational. But S alpha is contained in T alpha squared, alpha less than or equal to omega 1, non-deterministically as before. But it turns out that to carry this proof out properly, we have to do this deterministically. We're going to have to get deterministic about our constructions. In other words, no more Zornification, no more whatever, okay? So for this, we need a convenient well-ordering of T omega 1. And for this, we use an effective enumeration without repetition of Q01, namely P0, P1, dot, 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 just an enumeration without repetition, which has to start with 0. It has to start with 0. And we well order things according to double star, which is also just lexicographic. But this time the ordering on Q01 is of order type omega and not dense. Because we need to have, we're going to do a transfinite recursion. We're going to have something well ordered. Now we build the S alpha with E maximality canonically via the transfinite greedy process. Via the transfinite greedy process, where the stuff that comes up that we want to handle greedily is coming up according to less than double star. Less than double star is what feeds us the greed, the greedy feeding. We say that S alpha is greedy S maximal. the pairs of points are ordered from less than double star first by less than double star max, and then by less than double star lex. You see, in the greedy construction, we're going to have to be processing pairs of pairs. Pairs of pairs, the second pair being an ordinal and a rational. So less than double star doesn't tell the whole story. You just have to extend it to pairs and do that lexicographically. All right, so the pairs of points are well ordered this way, suitable for the greedy E-maximality construction. Transfinite, of course. We have to find 2 points, alpha 0, beta 0, that are going to act like the 1 and 2. We have to find 2 points in the space, alpha 0 and beta 0, which are going to act like the 1, 2 that we're looking for. Where we worry about the gamma p less than star alpha 0. We have to look at the parameters, which are going to be these points, gamma p, and we only have to worry about one parameter. Remember, this is in 2 dimensions, at most one parameter. Now, actually, this is a little bit misleading. We actually have to care about finding 3 points because I have to shift one up. You know, in the statement, it's going to ask for shifting. All right. Now, if you think about this, and you're a set theorist, this looks like subtle cardinals that I've got going on here. Looks like I need to have a subtle cardinal in order to be able to find these points that cohere, that do the right thing here. You see. Oh, I'm sorry. I kept talking about 3. I'm thinking about, I'm sorry. I'm thinking about, I said the word 3. I was thinking about the first statement where we're having indiscernibles. We were taking 3 tuples. No, I just have to worry about 2. I have to find a proper alpha 0 and a beta 0, which act like the 1 and 2 in the statement we're trying to prove. Right? But the if and only if, the statement says that alpha 0 and beta 0 are alike with parameters below alpha 0, right? I mean, it actually says 1 and 2 are alike with parameters below 1, right? In the rationals, right? But now we're in this space. Okay. Now that is exactly the kind of thing that subtle cardinals are needed to handle. So it looks like I'm lying to you about the fact that this is provable in Z3, but I'm not lying to you because we're going to use model theory instead of Ramsey theory. Now, don't worry. In the next lecture, we can only go, the model theory will only handle 2 dimensions. In the next lecture, we're going to use model theory, and on top of it, large cardinal common torques. Don't worry, large cardinal common torques dominates. All right. So how do we do this with model theory? We want to get an elementary chain under elementary substructure. Okay, so let's look at this construction. It's not the issue of the construction, it's the issue of let's pull out these magic 2 places. That's what we're trying to do. Pull out these magic 2 places, alpha less than beta. So let's look at S omega 1 contained in T of omega 1 squared. That's the setup we have when we built these transfinitely. And we formed the structure T star equals T omega 1 less than star less than double star. Put all our stuff in here. And S omega 1. That's a nice structure. Right? S omega 1 is a binary relation on T omega 1. Less than star is also a binary relation, namely the standard lexicographic product, which is dense. This is the dense thing. And less than double star is this well ordering. All right. The right endpoint is omega 1 comma 0, right? We now take a countable elementary substructure of T star. This consists of countably many alpha p, where alpha is less than omega 1, together with the right endpoint omega 1, 0. By a familiar argument, you can make sure that there are no gaps below omega 1, 0. You know this thing that occurs in model theory a lot, classical model theory, where you make an elementary substructure, it's got holes in it. You fill the gaps and get a bigger one, fill the gaps and get a bigger one, and so forth. And you make sure that there are no more gaps that way. You can do that. Yeah. Because you see, what's going to happen is when you take the elementary, you're going to get bigger stuff than you ever had before. You see. So that's what you can do this. All right. Now, this elementary substructure is K0, which is T star restricted to alpha P, where alpha is less than lambda 0 union this high point, omega 1, 0, this endpoint, right? So it's just the initial segment there, union this. Okay. So that's what K0 looks like. Now, since T star is greedy E maximal, K0 is greedy E maximal by elementary substructure. Obviously, if we change omega 1 to lambda 0 being the countable ordinal, then we would retain greedy E maximality. So this amounts to because this just amounts to an isomorphism. Hence, if we change omega 1 to lambda 0, we get our T lambda 0 less than double star S of lambda 0. It has to be that one because our construction was deterministic. There's only one thing satisfying a first order condition at every place. You see? This is similar to this stuff that Gödel did with the collapse stuff, in L, right? Except it's very focused here. Okay, so this is what we get. S lambda 0 at alpha P lambda naught 0 is if and only if S omega 1 alpha P omega 1 0, right? In other words, this is just because of the isomorphism, right? We get these three clauses. That should look, that are very close to what we want. Now we're close to done, and we finish by making things entirely countable. You can get around this last step, but it's not using Skolem-Lowenheim theorem downward and all that, but let's not do it that way. So we're close to being done. We finish by making things entirely countable. We can obviously perform the same construction again, getting lambda naught less than lambda 1 less than omega 1, such that for all alpha less than lambda 1, the above three that I just did hold with lambda 1 replacing lambda naught, right? And then we use transitivity of if and only if. I learned a long time ago that if and only if is transitive, right? And in fact, if and only if is an equivalence relation. All right, so we get this. That S lambda naught at alpha P lambda naught 0 is if and only if S lambda 1 at alpha P lambda 1 0, right? If and only, and also this and this, right? Because of the transitivity of if and only if. Because these things are like the big one. And now if you have a second one that's also like the big one, the two of them are like each other, that kind of idea. And this is the same shape as the required 1, 2, 3 that we're looking for. We just make an isomorphism from this situation into Q02 less than, sending lambda naught to 1 and lambda 1 to 2. Just make any isomorphism. Everything is dense. We don't have to worry about making an isomorphism with the less than double star, that well ordering, because that was just used as a technique to develop these structures. And we throw it away after we used it. So this has nothing to do with with less than double star. That was just used to define the transfinite recursion. With this line of reasoning, we can strengthen the invariance conditions 1, 2, and 3 considerably, because we actually prove much more than we need. We can obviously build a closed unbounded set of limit ordinals, closed unbounded set of limit ordinals, such that for all lambda less than lambda prime from the set and all alpha less than lambda, we have this equivalence. Because it's all elementary substructure stuff, and we just repeat what we just said. This doesn't belong there. Okay. Now, using finite initial segments of this W, we can obtain the following stronger statement. Let's take a look at what this says. Again, I have a set of a set of order types of 4 tuples, that there exists a set in Q0n to the squared, as before it was Q02 squared, with E maximality, where for all M less than R from 1 through N and P less than M, we can shift between M and R. You see? With the parameters yeah, I should have said, I'm sorry here. Oh yeah, P stands for rational. P less than yeah. You can even make it. Maybe you need to make it this way. Yeah. Okay. Right. The same thing that we did before. Okay. And this kind of invariance, this has been was discussed last time. It's a special case, with exponent 2. It's just exponent 2, where invariance is very simple. You're just moving one thing. Note this proof uses transfinite recursion on omega. Let's just show you how great my system is. Oh, I have to get the font. All right, let me not waste your time. Wait. There. See how wonderful it is? Okay, so, all right. Maybe you can't do that with text so easily. All right, so this is local. And Z3 is clearly more than enough. So we used omega-1 transfinite recursion omega-1. We played around with the end result of the transfinite recursion. And so clearly Z3 is more than enough. And exactly what you want to say is quite exactly enough. What fragment of Z3 is a question I think I once thought about and came to an answer, but I've forgotten the answer. So never mind. Z3 is all right. Now, actually, if you fix the interval n equals 2 and let the dimension be arbitrary, you also don't get into trouble because 2 is so small. And what are we actually saying? If I have a set of 2K tuples of order types of 2K tuples, I can find a set with the E maximality in 0, 2, where for every x in Q01, I'm using Q01 again as a parameter set, using singleton 1. If we change the 1s to 2s, then we don't change membership in S. Did I forget to say something important? Just 1 second in this one here. Yes, I lied. Um, didn't I? No, I didn't lie here. It's only in 2 dimensions. You can do this. The parameters are now all over the place, but because it's dimension 2, this is not. This is looks bad, but it's not. You can do this because you're in dimension 2. Yes, very important. Okay, let me continue here. So here you can do it in any dimension, but I'm only on 0, 2 because I'm only changing ones to twos and I'm in here, this space. And this will use the same thing that we did for the first construction, actually, except that we'll use double star for treating elements of T omega 1K. We construct we just need the first term of W, that closed unbounded set. We use Skoll-Ohnheim theorem, or alternatively use the first 2 terms of W to avoid Skoll-Ohnheim if you don't want to use it downward. So that one actually is more like the first construction than the second one, but they're all very related. So you can use dimension 2 and arbitrary numbers of indiscernibles, quote unquote, or you can use 2 indiscernibles, just 1, 2, and use any dimension, and the proofs will be very similar. You'll basically have the same stuff going on. You have to process that. It's great. So the first time in which we're going to look like we're in big trouble doing this, because remember, we relied on elementary substructure, elementary chains, not combinatorics, right? No combinatorics here. We did combinatorics we used, by the way, in the first stuff where it was probably reverses to it's where we used ACA naught. Remember, we used some combinatorics due to Ramsey. The second thing, we don't use that. We use a model theory, classical model theory. But now, what if K is equal to N is equal to 3? Then things need to be dealt with differently. Well, more elaborately is basically what I want to say. The model theory isn't good enough. We're left with something that looks like subtle cardinals. That's what happens. So that's what we're going to do next time. But I do want to say one more thing that's important. There's a weakened form of 1, 2, and 3 that we can do in Zermelo using combinatorics available in ZC. This is actually a prelude to the next lecture, and I don't have much time to talk about this, but I'll go through it quickly. Fortunately, in this beautiful statement, which has arbitrary numbers of indiscernibles and arbitrary dimension, oh my God, the parameters are in the interval Q0 1/2. You see the number 1/2? It's smaller than 1. This is important. That and the invariance condition is if I have order equivalent X and Y in this little interval together with the indiscernibles, then and they have the same coordinates in the same positions, less than 1. That means the same coordinates in the same positions, less than 1/2. Less than 1 is just a cute way of saving 1/1,000,000th of a penny by not writing 1/2. Okay, so all right, that S is an S if and only if Y is an S. So this is invariance, this kind of invariance. Yes, it's discussed in either the last lecture or it's in the book draft. This can be done because we use the model theory that we did, but then we apply the Erdős-Radó theorem because we're only partitioning into countably many pieces. See, 0, 1/2 is segregated as a countable set of parameters, you see. And we use the Erdős-Radó theorem with Beth sub t instead of omega 1. 2 to the 2, 2 to the 2 to the 2 to the 2, dot, 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 with Aleph naught at the top, right? The Erdős-Radó theorem. And we combine the model theory, classical model theory construction with the combinatorics layered on top that we can do in Zumelo. Okay. Now, what we're going to do next time is we're going to do the model theory first. What we're going to do next time is we're going to replace that 1/2 by the number 1. We're going to replace the number 1/2 by the number 1. That gives us our strongest statement in the book. That gives us our strongest statement in the book. And when we replace a half by 1, this statement, we're going to have to use large cardinal combinatorics, first the model theory, then the large cardinal combinatorics next. And there, I cared a lot about the reversal. I proved that I reversed that. Reverse that to con SRP. It's equivalent to WKL naught plus con SRP. All right, so it's now noon my time, and I'm finished exactly 1 hour. Andreas, you have the floor.
Yeah, thank you very much. I think I will now stop the recording and can go to the question.